Good morning and welcome back to the next session of the P block elements 2. In this session, we are going to look into the oxygen family and the reactions which is undergone by the oxygen followed by the ozone and the allotropes of the sulfur dioxide, the oxacids of the sulfur, all those things we are going to look into this session. Firstly, group 16 is an oxygen family and we call it as the chalcogens. This chalcogens, why do we name it as a chalcogens? Is because of the fact that it has an ability to form ore, which means most of the ore composed of this oxygenated. That's why it is called as ore forming elements. That is why it is called as chalcogens. And most of the ores, as I said, it exists in the form of an oxide or in the form of a sulfide. So both oxygen and sulfur belongs to the group 16, no doubt in that. Oxygen is the most abundant element and exists as a molecular oxygen, which is a dioxygen in air, which weighs about 20% in among the air. So that is what it is, 20% by weight by volume, it was stated. Then oxygen occupies a major part of the earth crust followed by the minimum part of the sulfur. 46.6% of the oxygen and 0.03% of the earth crust occupies by the weight. Then sulfur, which exists as an sulfides and it exists in the form of an sulfates, etc. As a sulfate, it exists in the form of a Epsom salt and the gypsum salt, and sulfide it exists in the form of an galena, zinc blende, pyrites, etc. And obviously, all the ashes of the volcanic eruption will result in the sulfur, deposition of the sulfur over there. The other elements of the family will exist as a trace amount and they exist in the form of an selenites and tellurites along with the sulfides of the oxygen and the sulfur, etc. See, so totally from the occurrence what we have seen, the oxygen belongs to the group 16. It is otherwise called as chalcogens. Why it is called as a chalcogens? Because it has an ability to form a ore, or I would say most of the ore composed of this oxygen in it. I said since most of the ore composed of an oxygen, then also some of the ore exists in the form of a sulfide. Fine. Oxygen is the abundant element. Then it exists as a molecular oxygen, dioxygen in air, weighs about 20% mass by volume. Then 46.6% of the earth crust composed of this oxygen, then 0.034% of the earth crust composed of this sulfur. Sulfur exists as in sulfides and sulfates. As a sulfate exists in the form of a gypsum salt and Epsom salt, and sulfide exists in the form of galena and zinc blende. And after eruption, volcanic eruption, the ashes composed of major part of the sulfide, the other elements of the family exist in the form of a selenite and tellurites along with the sulfides of the previous one. Its physical properties. If you look into the physical properties, the room temperature, oxygen will exist as a gas, the rest of the one exists as a solid. Atomic number, atomic mass, radius, melting point, boiling point, density obviously will increases from oxygen to polonium. Then isotopes doesn't been listed anything, so its elemental form is being listed here. Then electronic configuration, as I said, you have to have the very first element of the period and its atomic number, and followed by you can able to have the atomic number of those in the mind very clearly. You have if oxygen is 8, you need to add 8 to that so that you will get sulfur. From sulfur to selenium you need to add 18. From selenium to tellurium you need to add again 18. From tellurium to polonium you need to add 32. So similarly you will be able to get the atomic number of those elements so easily. Then to write the electronic configuration starts with the helium, neon, argon, krypton, xenon. Then the general electronic configuration, the valence electronic configuration of this family is ns2 np4. So starts from 2s to 2p4, 3s to 3p4. Before 3s nothing comes. Then 4s to 4p4. Before 4s 3d comes, 3d10 you have to write. Then 5s to 5p4. Before 5s 4d comes there, 4d10. Then 6s to 6p4. Before 6s 4f comes and 5d comes, 4f 14 and 5d10. So this is what the electronic configuration of those elements. Next one, oxygen. The preparation method of an oxygen includes its existence also. In atmosphere, 23% by mass of the oxygen you will be able to find. Among the atmospheric air, 23% by mass you will be able to find oxygen. In water, if you take H2O as 100%, out of which 83% will be oxygen. Total rocks that we have in our earth will have oxygen in the combined form. So oxides. So that is what is stated. So how do they prepare this oxygen industrially? By the fractional distillation of the liquefied air. Liquefied air. So you have to, when during fractional distillation, obviously the other gases will separate at a different temperature, so fractionally it can be distillated so easily. Then the decomposition of nitrogen peroxide can also be done, and it is considered as a laboratory preparation method. Laboratory preparation of the method, hydrogen peroxide includes H2O2, the presence of an MnO2 decomposes to give water molecule and molecular oxygen to balance with and make it as 2. Then this oxidation with the potassium permanganate. Here manganate ion MnO4 minus, in which the oxidation state of the potassium is +7, and it changes to Mn2 plus, which means manganese have been reduced. So hydrogen peroxide on treatment with permanganate ion and the proton, you will be getting the molecular oxygen O2, then H2O is your product. So if I make it as 5 here, so hydrogen, oxygen becomes 10 here. So if I make it as 2, manganese becomes 2, so I will make it as 2 here, plus 2 Mn. So I need to check with the hydrogen and oxygen, so finally we can balance it. Hydrogen is 10 here, we'll find out with the oxygen. 10 plus 8, 18. 18 there, so here it is oxygen. If I make it as 6 hydrogen, so it is 3 H2O. Otherwise, if I make it as an 8 hydrogen here, so here it is 4 H2O. So oxygen I need to balance further. So 10, again 8, 18. Out of 18, 4 is balanced. So I have to make 14 here, so it is 7 O2. So in such a way we can balance it. Next one. The decomposition of the oxides of the metal oxides, will result in the formation of this molecular oxygen. Mercury oxide decomposes to give molecular oxygen. If I make it as 2 here, here it is 2, balanced. Then barium dioxide, barium plus molecular oxygen on heating. Potassium chlorate, 2 molecules will getting 2 KCl plus 3 O2. Potassium nitrate, it is converted into KNO2, potassium nitrite, then molecular oxygen will go out. So this is how the molecular oxygen has been prepared here. Then regarding the properties of this oxygen, it is a diatomic and obviously it's a paramagnetic. Since you are all studying 12, in the 11th itself you would have know what is called paramagnetic, what is called diamagnetic from the molecular orbital theory. So from that it is very clear that it is a paramagnetic and it's a diatomic gas. Then it has an ability to form a strong hydrogen bond like nitrogen, fluorine, etc. Then followed by the allotrope forms of this oxygen can be a diatomic and a triatomic, which means it exists as a molecular oxygen, then followed by the ozone, that's called trioxygen. Then you will be able to find this molecular oxygen in the negligible amount, or the ozone you can able to find in the sea level as a negligible amount, which means very small amount of the ozone you will be find over the sea level. That is what. That has been formed by the action of the UV light in the atmosphere. Because of the UV light, a molecular oxygen breaks. So thereby nascent oxygen creates. Nascent oxygen will again react with the diatomic oxygen and forms an ozone. So this is what. We have that reaction. This is what the reaction. A molecular oxygen will break to give the nascent oxygen, and the nascent oxygen will combine with the molecular oxygen to form a ozone. This is what actually happens. Okay. See, through the laboratory we can able to prepare ozone. When we prepare ozone with the help of an electric discharge by creating 20,000 volt, out of the oxygen that we have taken, only 10% of the oxygen has an ability to convert it into ozone. So, since only 10% have been converted into ozone, the mixture composed of both oxygen as well as ozone, that's why it is called as ozonized oxygen. Okay, right. So, O2 will form O3. Not all the O2, only 10% of the O2 will definitely form what? O3. So, this is what. So, I will take this way. Okay. This pure ozone exists in the form of a pale blue gas. Okay, pale blue gas, and it has been obtained by the fractional distillation of the liquid ozone and oxygen, which means whatever we have got here, I have to fractionally distillate it, so that ozone distills at a different temperature, oxygen distills at a different temperature. So this is what. The preparation of methods of the ozone, as I discussed already, it forms a nascent oxygen further reacts with the molecular oxygen to form a. Then regarding the structure of the ozone. Structure of the ozone includes, it's a bend shaped or V shaped, I would say, and the electrons are symmetrically delocalized between the oxygen atoms, which mean with the help of Lewis dot structure we have plotted, since both the oxygen on the either side has a similar nature, either the negative charge can bear with the right side oxygen atom or it can bear with the left side oxygen atom. So this is what regarding the structure of the ozone, which means the pi bond can be delocalized between the three oxygen atoms. Next one, chemical properties. See, oxygen is an ability to react with a metal or non-metal and forms an oxides. Mostly, if you look there, the metals like, or I would say alkaline metal or alkaline earth metals reacts with the oxygen at the room temperature itself. Firstly, then the less reactive metal reacts with this oxygen as a finely powdered, okay, as a finely powdered in the room temperature. See, for alkaline metal it is not necessary to powder it, but whereas the less reactive metals has to get, if it has to react with the oxygen, you need to first make it as a powder. Only after making it as a powder, you will be able to find that its reaction with the oxygen at the room temperature. This finely powdered ore of the finely powdered metal is called as a pyrophoric. This pyrophoric, when set on fire, it can liberate a large amount of energy. So exothermic reaction will take place. It is set to fire. Okay. So this is what regarding the chemical properties. That too, it's quite important. What is called pyrophoric? Question may be asked. So you can say the less reactive metals has an ability to react with an oxygen to the room temperature as a finely divided ore. A finely divided ore is called as pyrophoric, which when set on fire, exothermic reaction takes place. Lots of heat energy will be released. So we can say that. Then ozone is a powerful oxidizing agent, no doubt in that. See, wherever oxygen cannot act as an oxidizing agent, ozone can oxidize it. So this is a notable one. If oxygen cannot oxidize something, ozone can oxidize it. So that is what the statement talks about. And this ozone can oxidize as potassium iodide to iodine, and this is widely used to estimate the quantitative of ozone, how much of ozone is present. We can able to estimate with the help of the reaction. See, ozone on reaction with the potassium iodide, O3 plus Ki plus H2O gives potassium hydroxide plus molecular oxygen plus iodine. So iodine is 2 there, so I will make it as 2. Potassium here it is 2, so I will make it as 2 here. Then I need to check with the oxygen. Oxygen 4, here also it is 4. Hydrogen 2, that's all, equation is balanced. Okay. Then see, because 2 moles of potassium iodide can reduces this ozone to molecular oxygen. So if the number of calculating the number of moles of potassium iodide reacts with the ozone, we can able to find how much of ozone that is present. That is what it is stated. It is quantitatively used to measure the estimation of the ozone. So that is what. Then ozone is used to oxidize the organic compounds where oxygen cannot do it. Then in acidic solution, ozone exceeds the oxidizing power of this oxygen as well as fluorine here. Then in the rate of decomposition actually drops slowly in the alkaline solution, which means in alkaline solution ozone is more stable. So this is what assertion and the reason type of question can't be asked from this point. See, the rate of decomposition of the ozone actually drops slowly in the alkaline medium. So this can be asked as an assertion. So you have to take a note of it here. See, acidic solution, ozone actually exceeds the oxidizing power of the fluorine as well as the molecular oxygen. In basic solution, it is more stable, which means decomposition takes place very slowly there. Then uses of an oxygen, it is very important for the survival of the living organisms. Then in oxyacetylene welding, which is where in order to generate a more amount of an energy, combustion reaction has to take place. In order to further increase the combustion rate, oxygen can be supplied in the welding for the welding purposes. So that's why it is called as an oxyacetylene torches. Liquid oxygen is already used as a rocket fuel. So these are all being noted. See, so to sum up regarding the ozone, ozone is the one which has been prepared by forming the nascent oxygen. The nascent oxygen will further react with the molecular oxygen and forms a ozone. The properties of the ozone include it's an excellent oxidizing agent. Where oxygen cannot oxidize it, it has an ability to oxidize it. The quantitatively it can able to measure the ozone with the help of a potassium iodide. This is one. The estimation processes. This is what. In acidic solution, it exceeds the oxidizing power of the fluorine as well as the molecular oxygen. the rate of decomposition of the ozone slowly drops in the alkaline solution in the basin. So this is regarding. Then next one, allotropes forms of sulfur. See, sulfur can exist in the form of a crystalline as well as amorphous. In amorphous form, it exists in the form of a plastic sulfur, milk of sulfur and colloidal sulfur. In crystalline form, it exists in the form of a rhombic sulfur and monoclinic sulfur. See, have a note. Sulfur exists as a crystalline as well as amorphous. In amorphous, it exists in the form of a plastic sulfur, milk of sulfur and colloidal sulfur. Then in the crystalline form, it exists in the form of a rhombic sulfur and monoclinic sulfur. Among these allotropes of the sulfur, the one which is thermodynamically more stable is the rhombic sulfur in the room temperature and the pressure. Okay, this exists in the form of an yellow color crystal, and sulfur will exist in the form of an S8 crystal. Okay, just like a crown shape. Sulfur will exist in the form of an S8, just like a crown shape. See, yes, 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 yes. So this is what? Okay. So S8 you will be fine, and this is, since it exists in the form of a crown shape, so it exists in the form of S8 molecules. This rhombic sulfur alpha form can be converted into the monoclinic sulfur beta form by increasing the temperature above 96 degrees Celsius. If the temperature goes beyond 96, rhombic sulfur will not exist as a rhombic sulfur, it will change into the monoclinic sulfur. Then if you reduce the temperature below this 96 degree, beta sulfur will convert into the alpha form. So this is what usually happens here. See, as like this rhombic sulfur exists in the form of a S8 molecule, this monoclinic sulfur also exists in the form of an S8 molecule, and some of them will exist in the form of an S6. Along with the S8 molecule, some of the sulfur will be accumulated in the form of an S6. And this monoclinic sulfur exists in the form, resembles like a needle like a prism, we call it as a prismatic sulfur. It exists in the form of a needle, and the end you will be able to find the prism. So this is what is this prismatic form. And the stability of this monoclinic sulfur actually lies between 96 degree to 119 degrees Celsius. When the molten sulfur is the melted one, is treated with the cold water, you will be able to get the plastic sulfur. The plastic sulfur which exists in the form of a rubbery ribbon, yellow color. Okay, so that's what I have written it as an yellow rubbery ribbon. See, I have to heat the sulfur, and to the sulfur I need to add this cold water. If I add the cold water, it is converted into plastic sulfur. So it exists in the form of an yellow rubbery ribbon color. So this is regarding. Then plastic sulfur, since it exists in the form of an yellow rubbery ribbon, it will be very soft, no doubt in that. Since the rubbery form, it can be stretched so easily. Then on cooling, it becomes hard, it changes back to the rhombic sulfur. See, this plastic sulfur is prepared from the molten sulfur. On cooling, it directly goes to the rhombic sulfur, because temperature will go below 96 degrees Celsius. That's why it goes to the rhombic sulfur. Okay, so this is regarding that. Sulfur can exist in the form of a liquid state as well as the gaseous state also. Okay, this is the additional point. Sulfur exists in the form of a liquid state as well as gaseous state also. When the monoclinic sulfur is heated to 140 degrees Celsius, it converts into the new allotropic form called lambda sulfur, which is a mobile pale yellow liquid, a liquid which can flow. That's what mobile pale yellow liquid. See, usually over the liquid sulfur, you will be able to find the gaseous sulfur over there, out of which 90% of the sulfur exists in the form of an S6, S7, S8, and the remaining exists in the form of an S2, S3, S4, S5. Okay, right. So this is regarding. So to sum up, I'll go from the beginning. The allotropes of sulfur composed of two types. One is amorphous and the crystalline. Crystalline sulfur contains rhombic and the monoclinic. Amorphous sulfur contains plastic, milk of sulfur and the colloidal sulfur. This rhombic sulfur is the thermodynamically stable form at the room temperature and the pressure, and it exists in the form of an yellow color crystal. The sulfur will exist in the form of an S8 molecule. Rhombic sulfur alpha, which is called alpha form, can be converted into the beta form monoclinic sulfur when I raise the temperature above 96 degrees Celsius. If I cool below 96 degrees Celsius, monoclinic sulfur gets back to the rhombic sulfur. This monoclinic sulfur, if you look into it, S8 molecules will be present along with the S8, S6 molecules also will be present there. This is one thing. Then it exists in the form of a needle-like prism. That's why it is called as a prismatic form. And this is quite stable between the 96 degrees Celsius to 119 degrees Celsius. Then this molten sulfur, when it is treated with the cold water, it is treated with the cold water, it gives the plastic sulfur. The plastic sulfur exists in the form of a yellow color rubbery ribbon, very soft, can be stretched easily. Then if I cool this, it becomes hard. Since temperature goes below 96 degrees Celsius, we will be getting the rhombic sulfur here. Then sulfur exists in the form of a liquid as well as gaseous state. If the molten sulfur is heated to 140 degrees Celsius, you will be getting a lambda sulfur, which is a mobile pale yellow liquid. The vapor over the liquid sulfur contains S2, S3, S4, S5 along with S6, S7, S8 as a larger amount 90%. So this is regarding the allotropic forms of the sulfur. The next one what we have got is sulfur dioxide. The preparation of the sulfur dioxide actually includes, it is easy to prepare the sulfur dioxide by treating with the oxygen, molecular oxygen. The large scale production is done by burning the sulfur in air. Nothing, we are just sulfur will treat with the oxygen to form sulfur dioxide. Okay, then sulfur can be reacts with an oxygen to form sulfur trioxide also. Okay, so it is 3O2, so it is 2, so it is 2 here. So to balance with, see, this is a notable one. 6 to 8% of the sulfur is oxidized to what? SO3. Out of all the sulfur that we have taken, completely do not get undergoes oxidation. Out of 100%, only 6 to 8% will undergo oxidation to form SO3. So that is regarding. Then the other preparations includes the formation of the sulfur dioxide. The sulfide was like a galena and zinc blend. We have seen this reaction in the unit 1 itself, metallurgy. When it is roasted in air, we will be getting a sulfur dioxide over there. This sulfur dioxide that has been formed is widely used to prepare the sulfuric acid in the industries. Sulfur dioxide, wherever it goes as a gas, it is a global warming gas. SOx, it comes under the category SOx. So we cannot just easily leave without sulfur dioxide in the atmosphere just like that. So instead we need to convert it into the other useful form. So that is why it has been used to prepare the sulfuric acid. Then zinc sulfide. This reaction we have seen in unit 1 itself. ZnS plus O2 forms ZnO plus sulfur dioxide. So to balance with, I'll make it as 2. I'll make it as 2 here. So it is 3. Then ferrous sulfide, iron pyrite, I'll take FeS2, reacts with an oxygen to form ferric oxide, FeO plus SO2. So I'll make it as 2 here. Iron becomes 1 here. So I cannot balance the stoichiometry. I'll make it as 2. So sulfur becomes 4. So I'll make it as 4. Oxygen becomes there 10. So it is 5 only. That's all. So regarding this method of preparation, this is quite a familiar one. We have seen in the first unit itself. Then the laboratory preparation includes the reaction between sulfuric acid and the metal. Okay, when the metal or metal sulfide reacts with the sulfuric acid, the resultant product will be getting sulfur dioxide as a byproduct. See, the copper reacts with the sulfuric acid H2SO4 to form copper sulfate CuSO4 plus sulfur dioxide plus water. So to balance with, here it is 2 sulfur. So if I make it as 2, hydrogen becomes 4 there. So I need to make it as 2. Okay. So I need to check with the oxygen 8, 4 plus 2, 6, 6 plus 2, 8. Equation is balanced. Then sulfite ion SO3 2 minus will react with the proton H plus. This will form a water and sulfur dioxide goes out. So when there is a metal sulfide also, reaction will go like this. Okay. Then regarding the properties of the sulfur dioxide. The properties of the sulfur dioxide, if you look into it, it exists in the form of a gas. Okay, firstly it exists in the form of a gas. Sulfur dioxide is mildly deposited from the volcanic eruption, and various power plants, which includes the coal, oil and copper melting plants, a large amount of sulfur dioxide will be released, and that will be definitely utilized to prepare the sulfuric acid, no doubt in that, because it cannot be exposed to the atmosphere. Then it's a colorless gas and it has a suffocating odor, and it is highly soluble in water, which can dissolve in water so easily. It is 2.2 times heavier than air. Here air talks about the oxygen. Okay, that's why it is 2.2 times heavier than air. Sulfur dioxide in the gaseous form can be liquefied at 2.5 atmosphere and 288 Kelvin. If the temperature and the pressure is maintained as such, you can able to liquefy this gaseous sulfur dioxide. The boiling point of the sulfur dioxide is 263 Kelvin, which is quite known to us. Then the chemical properties includes SO2 is an acidic oxide, so it reacts with the water and forms a sulfurous acid. So SO2 plus H2O, it forms H2SO3. So direct combination. The sulfurous acid that has been formed, further split up into proton and sulfite ion. Okay. So since the sulfurous acid is quite unstable, so it decomposes to give proton and the sulfite ion. Okay. Then the reaction with the sodium hydroxide and sodium carbonate. Sulfur dioxide reacts with sodium hydroxide to form sodium bisulfide, NaHSO3. So Na1H1 sulfur 1 oxygen 1 equation is balanced. Then sulfur dioxide reacts with the sodium carbonate, Na2CO3 plus water to form sodium bisulfide, NaHSO3 plus carbon dioxide. So sodium here it is 2, so I will make it as 2 here. Hydrogen is 2 there. Then sulfur here it is 2, so if I make it as 2 here, sulfur is fine. Carbon 1, I need to check with the oxygen here. Oxygen 4 plus 3 7, 7 plus 1 8, 6 plus 2 8, equation is balanced. The next one is next one. The sodium bisulfite form decomposes to SO3 plus SO2. So to balance with sodium there it is 2, so I need to make it as 2 here. Balance. Then regarding the oxidizing property of the sulfur dioxide, sulfur and water molecule H2O. Okay, so here oxygen is 2, I need to make it as 2 here, so that 2 hydrogen will take up the 2 oxygen and mix as 2 water molecule, so will make it as 3. Then oxide and sulfur. Okay, so oxygen is 2, so I will make it as 2 here, I will make it as 3. See, ion which is 0 to plus 2 oxidation state. Okay, so that's why we are saying that it has an oxidizing property. The next one, reducing property. This sulfur dioxide reacts with the water molecule and chlorine to form sulfuric acid along with hydrochloric acid, H2SO4 and HCl. So I need to balance it. Chlorine here it is 2, so I will make it as 2, fine. Hydrogen there it is 4, so I will make it as 4 by making it as 2 here, fine. Sulfur 1, oxygen I need to check, 2 plus 2 is 4, there also it is 4, equation is balanced. And second, sulfur dioxide along with the water, potassium permanganate, KMNO4, it forms potassium sulfate, K2SO4, MnSO4 plus. Okay, so to balance with potassium here it is 2, so here it is 2, so I will make it as 2 here. So I need to check with the sulfur. If sulfur is checked, equation is done. Sulfur there it is 4, right side it is 4, so oxygen right side 12 plus 4, 8 plus 4. So I need to develop the stoichiometry, no other go. To do that, let me increase this water molecule further. If I increase the water molecule like by making it as 5, so if I make it as 5 there, 8 plus 5 13, 13 plus 8 is 21. 12 plus 4 16, so it can be done. Sulfur dioxide plus water plus potassium permanganate plus MnSO4 plus H2SO4. Right. See, so it's an oxidizing nature. So I need to check with the first, I need to check with this potassium. Here it is 2. So I will make it as potassium is 2 here, here it is 2. Manganese is 2 here, so I will make it as 2 here. Then hydrogen 2, 2, fine. But the thing is, here it comes with an odd number. So right side you have an even number, so it can't be balanced. I have to double up and make it as an even number. That's the only possibility that I could do. So if I make it as 2 here, hydrogen becomes 2 there, so I'll make it as 4 there, here it is 4. Now check with the sulfur. Sulfur 2, 4. If I make it as, it is sulfur is fine, hydrogen is fine. Oxygen 8, 8, 16, 16 plus 4 is 20. Okay. Here it is 8, 8 plus 2, 10, 10 plus 10, 20. Equation is balanced. The only thing is, you have to make sure that both sides we need to, while balancing, oxygen has to be in the even number. Okay. So in order to make that, I have to make this hydrogen as 2. Water molecule as 2. That's it. Like that. Next one. Reaction with potassium dichromate. Potassium dichromate K2Cr2O7. It forms potassium sulfate K2SO4 plus chromic sulfate Cr2SO4 thrice plus H2O. So let me check. Potassium 2, 2, chromium 2, okay, fine. Sulfur I need to check. Sulfur, if you look here, 3 plus 1 is 4. I need to check. 4 plus 1, 5. 5 plus 12 is 17. Equation is balanced. Then, this sulfur, and it is very clear, it is widely used to prepare the sulfuric acid. We have seen that. The next, dioxide. Because it has a reducing nature, sulfur trioxide in water actually reduces the colored substance to the colorless one. It has an ability to bleach the wool, silk, sponges, straw, etc. Because of the production of hydrogen by the sulfur trioxide, it has the ability to reduce, or it has the ability to decolorize the colored substances. So SO2 reacts with H2O to form been formed a nascent. So the nascent actually changes to the colored substances. See, this action of this sulfur dioxide is not at all permanent. When the bleached product is exposed to the air, it reattains the color, which means it takes the atmospheric oxygen and it gets back to the original color. That's why the bleaching action of the sulfur dioxide is very temporary. Okay. The next one, uses. Uses is it has an ability to bleach air, silk and wool. Okay, the colored substances like it can bleach, and used to infect crops and plants in agriculture. See, in the insecticides, a part of this insecticides includes the sulfur because it has an ability to disinfect crops. Okay, so agriculture purpose it has been used. Now, the very first one, here it is S double bond O, OH. Okay, so this is H2SO3, H2SO4, S double bond O, OH, OH, double bond O. H2SO5, which is OH, OOH. So this is H2SO5. Then H2S2O3, OH, S, double bond S, double bond O. So this is H2S2O3. Okay. The next one, H2S2O4. The H2S2O4 is S double bond O, S double bond O, OH and OH. So this is H2S2O4. The next one, H2S2O5, S double bond O, S double bond O, OH, OH, double bond O. So this is H2S2O5. The next one, H2S2O6 is S double bond O, S double bond O, OH, OH, double bond O, double bond O. So this is H2S2O6. Next one, H2S2O7. I'll write here. Okay. S double bond O, S double bond O, OH, OH, double bond O, double bond O. So totally here it is 6 oxygen, 1 oxygen will be present in between. Okay, so this is H2S2O7. The next one is H2S2O8. Okay, H2S2O8 is, we have an peroxide linkage and S double bond O, S double bond O, S double bond O, S double bond O, then OH, OH. So this is H2S2O8. And the last one is H2SN plus 2O6. See, S n times. Okay. Then 2, which means Sn I have written, I had to write 2S again. So S, S. H2. So it is OH. Here it is OH. Then how many oxygen there? 6 oxygen. 6 oxygen out of 6, 2 have been done. I need to make it as 4. So this is the formula for, structural formula for H2SN plus 2O6. See, so today's content, what we have seen is, we have come up with what is called this oxygen and how it has been prepared, and the allotropes of sulfur we have seen, then followed by sulfur dioxide we have seen as a major contented, and from the sulfur dioxide the very important question is the bleaching action of the sulfur dioxide is the very major question that is asked, and we have come with the oxo acids of the sulfur. See, you have to get practiced with the equation then and there itself. It is very difficult to collectively study this P block elements too, because you will get exhausted while balancing itself. So the reaction between the phosphorus and the nitric acid, such kind of the reaction, you can able to have the stoichiometry in the mind so that you can able to balance it so easily. But the reactions like this you can able to balance by spending a little bit of the time. Okay. So see you all next video in the following